Hello, this is Kun Zhang from Philosophy Department, and I hope you are well. So in this lecture, as well as the next one, you will see something about causality. Essentially, you can see why we have to use causality, how causal models are related to graphical models, and how we can discover causal information, and how we can infer the causal effects given the causal structure and some observational data. And finally, you can also see why it's really essential to do something called counterfactual inference. And then you can see what we can benefit, how you can do so, and what you can benefit from those operations. So if you have questions, please directly raise your hand or just send a message to the TAs. So I would be very happy to take questions because there are so many concepts. I really want to make sure we'll be on the same page. Okay. So we know that in our daily life and also in scientific discovery, we really have to distinguish between causal connections from associations. Right here, you can see a very simple example in the telegraph that said couples who share housework are more likely to divorce. Right? This sounds very astonishing. Why? And when we see this kind of information, we want to go further because we want to get something that is useful, that is helpful, right? And it's not surprising that there was a lot of follow-up discussions. Right here, you can see they try to see whether sharing housework really leads to divorce. You want to see the causal connection because if you just see association, you don't know what to do. But once you see the causal connection, you know, oh, to achieve that goal, I should do this. And here, this caricature basically explains my experience. First of all, generally speaking, causality implies dependence. And I think all of you are familiar with the propaganda in statistics, which says causation implies correlation, but correlation doesn't imply causation, right? So basically, it's correct, but maybe you want to make it more informative. And now we can say causation implies correlation, but correlation doesn't directly imply causation. However, in many cases, by making use of the dependence structure, dependence pattern, or some the distribution over multiple variables, you can really discover some information of causation from the dependence pattern, including the correlations. So if you look at this character, you can see, oh, when we were very young, usually we used to think that correlation implies the causation, right? I can still remember that when I was very young, sometimes, yeah, if I saw a very strong coincidence or correlation, I would like to say, oh yes, they are related. If I change this one, that one will change. And then later, after taking some classes, statistics classes, I changed my mind. But after doing research in this field for some time, now I'm very optimistic. Essentially, we can say that in almost all situations, by analyzing observational data, which gives you the dependence pattern, you can really find the causality under some assumptions. So we'll make the assumptions very, very clear to everyone. What's association? So essentially, if two variables are not independent, then they are associated. They are the way for them to be related. Or if you make a prediction, you can see one variable would be useful for you to predict the other. When we say X is the cause of Y, we have to go to another level. Right? We cannot just use the association because causality is a property of the process, underlying process. So what do we mean by X is the cause of Y? Basically here, you can see at the bottom, this is the definition. First of all, we have to define a particular change of the system called intervention. So we define causality based on the notion of intervention. Here, the definition says the following thing. If you do intervention on X, right, and you have two different values for X, which are X1 and X2, and you find that the corresponding distribution for Y could be different, as you can see from this equation, then you say X causes Y. So this is the definition based on intervention. Now, what's the definition of intervention, right? So intervention is defined this way. If you want to intervene on X, then in the system, you can only change the variable x without changing any other variable, at least for the moment. So if you want to intervene on x, make sure you just change this variable. And this action, make sure this action will not change any other variable. Now it's very natural to see why this is the definition of causation, right? In the system, this action changes only the value of x. And then you see a change in the distribution y, right? Since basically all other variables have the same value, then you can see the distribution, the difference in the distribution y must be caused by the difference in the value of x. Then you can say, oh, x causes y, right? So this is the intervention-based definition of causation or causality. So if you have questions, please just raise your hand because I'm paying attention to the participant window right now. I want to see whether you have questions. Okay, so now let's try to see a lot of phenomena by making use of the notion of intervention. Here are two examples. On the left, you can see we want to see the causal relation between two things. One is hot weather, the other is high sales of ice cream. Are they causally related? Is one of them is the cause of the other? So how can we verify that? Usually, we can easily determine causal relation at least for two reasons. First of all, in our experience, right, we still remember or we can imagine the effect of interventions. Second of all, we have temporal precedence information in most situations. So here, you can think of intervention. If you find a way to change the first event, right, to make it very hot, then you can see, oh, it's very likely that the ice cream, you will see the high sales of ice cream, right? So you can see, oh, if I change A, if I intervene on A, it's possible to see the change in B. However, you can find a way to intervene on B without changing A at all, right? So you can just hire a lot of people to buy ice cream, right? And then you cannot see the hot weather as a consequence of that. So here we can say, hot weather is the cause of high sales of ice cream. Clearly, we can have noise in the system, right? They are not necessarily deterministically related, and we'll come back to this point later. And now let's have a look at a second example. Here, suppose this guy goes to work by bus in the morning. So around 8:30, this guy is leaving home. At the same time, the bus is coming. So if you think of those things as binary variables, right? If this guy is leaving home, this variable takes value 1, otherwise it takes value 0. Then you can see the two variables are clearly related or correlated. They are dependent. Now the question is whether they have a direct causal influence in between. So do you have any idea? Just try to think of the relationship from the perspective of interventions. Any input? Any response? They are clearly related, right? Do you think they are causally related? Do you think one of them is the cause of the other? Okay, I see something. Yeah, so yes. Sorry, I cannot see your name. I only see the email address. Yes, the bus causes the man to leave. Okay, so suppose this is the case. What does it mean? First of all, intuitively, it does not seem to be the case. Why? Because the man does not see the bus coming, right? There's no physical way for them to be related. Then why do you think a bus coming will cause the guy leaving home, right? So clearly they are related. Now let's try to do interventions. What's the intervention? We have to change the target variable, only the target variable by the action. So now the bus is coming. You want to do intervention. Of course, this is very dangerous, but suppose you can do this, right? I can do this. I just simply jump in front of the bus, right? Hopefully the bus will stop. This is very, very bad. But this action will not directly change any other variable in this system, right? And then you can say bus will stop, but this guy will still leave home as usual. right? And similarly, when this guy is about to leave home, I just simply close the door. This is also intervention because this action will not directly change the bus coming. And as a consequence, you can see, oh, this guy will stay home while the bus will still come as usual. So if you think of the intervention, you can see there are no causal relation between them. Then how can you explain the dependence? Basically here, we have a common cause. Hopefully the common cause is something like a bus timetable. Both of them operate according to the bus timetable, right? And now you can see we have to really pay attention to the definition of intervention. Why? Let's suppose I do the following change. I want to change the first thing. I want to change the time that the bus is coming. What can I do? I just directly change bus timetable, right? As a consequence, I can change the first variable. However, this is not an intervention because this action will also directly change the second variable, which is about whether the guy is coming leaving home. So this is not a valid intervention. Although by this action, I can see the difference. I can see the change in some other variables. I cannot say anything about causality, right? Because all of them can be caused by my single action. So make sure it's intervention, and then you can see the causal relations by making use of interventions and the effects. Okay. So usually we use directed graphs to represent the causal relations. Sometimes the graphs can be cyclic, and we'll talk about that point later. So usually we use a direct cyclic graph, and I think Erica has been talking about the DEX for quite some time, so you are familiar with that. If you have a direct edge from A to B, basically it just means that A is a direct cause of B relative to this set of variables. So this is very intuitive, right? Okay, so in this class, I'm going to talk about, I just talked about definition of causality in terms of interventions, and I'm going to talk about what we can benefit from causal thinking, or why we should use causal thinking. In some situations, very intuitive, but in some cases, maybe we should need to think a little bit about the process and the causality. And you will see the difference between causal graphical model and graphical models. Essentially, you have to enforce some additional constraints or assumptions to make sure that the graphical model is causal. And then you can see the basic idea of identification of causal effects. And finally, you can see why and how to do counterfactual reasoning. And in next lecture, you will see how we can do causal discovery and the implication of causality in machine learning. So first of all, I think everyone knows that we have to distinguish between dependence and causality. If you just want to make passive prediction, giving ID data, then probably it's fine, right? You can just make use of data, you can forget about causality, dependence will be enough. But if you want to change something, or if you want to change the system to achieve your goal, you have to care about the causality. And this example discussed by Fisher a long time ago. You can see if you want to change the incidence of cough, right? You cannot make use of the correlated variables, which include yellow fingers. You have to go to the causes. Here, smoking is a cause, so you have to go to that level to achieve your goal regarding the incidence of some disease, for instance. That's very clear. And then let's have a look at the example called the Simpson's paradox. Here you can see a real data set published in the 1970s. So basically in the hospital, we have two groups of patients with kidney stones. One of them has small stones, the other has large stones. So we have two groups right here. Oh, 1 second. The system is very slow. Okay, so right here we have small stones, and then here we have large stones. We have two groups. And also we have two treatments, A and B right here. So you can see that for each group, treatment A is better than B. As you can see from the higher recovery rate. Here is 93% versus 87%. And for the other group, it's 73% versus 69%. So in each group, A is better. However, if you just merge the data, now you can see, oh, for the data consisting of both groups, B seems better because of the higher recovery rate. So now comes the question. Suppose you are a doctor, and suppose that you only care about the recovery rate. You just want to maximize the chance of recovery. Now, given a new patient, would you like to recommend A or B? Maybe you can just do a quick vote, or you can just write, you can use yes, no. If you want to go with A, please use yes. Otherwise, just click on no. I see yes, no. Could you go ahead? Okay. So I can see more A than B. Good. So basically now I can see, I will click. So there's a first click on participants, and then you can see yes, no buttons. Okay, good. So now this is the reason why we call this problem paradox. If I know that the stone is small, I would say A. If I know the stone is large, I would say A, right? And if I only care about the last row of this table, I would say B. It's a contradiction. So I would recommend A or A, which turned out to be B. That's why it's paradox. Of course, you know, what I just said is not really accurate, because in principle, even if I have no idea about the size of the stone, I should still recommend A, because A is always better. In this case, we see this very strange phenomenon just because of the relationship between correlation and the causal effect. Intuitively, when you make a recommendation right here in this graphical model, you only care about the property of the causal influence of treatment on recovery, only the line, the solid line. However, the correlation between treatment and recovery can be rather arbitrary because of the third variable, stone size, which influences both of them. So here we say stone size is the direct common cause of treatment and recovery. Because of this common cause, the dependence pattern between treatment and recovery could be rather arbitrary. As a consequence, you cannot clearly see the causal influence of treatment on recovery right here, right? Oh, right here. You cannot clearly see the property of this connection from the dependence pattern. Okay, so this is a very important problem, and there are so many related examples. So here you can see. Oh, I'm learning how to give lectures this way. Let me see. Okay, now you can see another example. So on the left, you can see the scatter plot of exercise and collateral given each age group, right? And you can see for each age group, on average, the more exercise you do, the less collateral you are going to have. That's good. That means, oh, I should do more exercise. However, if you ignore the age information, you can see the distribution of exercise and collateral on the right. They are clearly positively correlated, right? So that means, oh, according to the data, according to the distribution, the more exercise you do, the more collateral you are going to have. You can see it's very strange. So basically, the second statement is, okay, let me see, there's a question. Why the group size are different? Probably the group size Yeah, you are totally right. So basically, the question is about the group size. Let me go back to the question. Let me go back to the first example. You are totally right. Right here, you can see stone size is a direct cause of both recovery and treatment. And if stone size causes only one of them, then it's not a common cause, not a direct common cause. Then there are no such phenomena. You are totally right. And later you can see that in order to identify causal effects, we just want to do something like what you just suggested. Perfect. Okay, so in this example, you can see something similar, right? Oh, if I know the age information, I know, oh, they are negatively correlated. But if I don't know the age information, they are positively correlated. However, if you make a recommendation, right, in this case, if you make a recommendation, you have to go to the causal level because you want to change something, you want to achieve your goal, or you want to improve something. Okay, so that's a second example. And the third example is about some particular type of dependence in the data. So let's go back 60 years in America. Probably you would find that female students are kind of smarter than male students on average. Why? We believe that according to the whole population, female and male are kind of equally smart in some way. Now you can see this kind of strength dependence. Why? Essentially, this is because of selection. And if you work with internet data, right, you always have this issue. So in this case, you can see gender and IQ at this moment are both causes of being admitted to college. Although they are independent at the beginning, according to the population, once you have the common effect, which is being admitted to college. Once you know this, given that they are college students, then they will become dependent. Gender and IQ will become dependent in most cases. So this is because of selection. And if you only see the selected sample, you will see this dependence between gender and IQ. And if you go to the whole population, this dependence relationship will disappear, right? And in most cases, you want to analyze the given sample to say something about the population. That's why you should pay attention to the selection and try to find a way to correct for such a selection bias. And right here, you can see another related example, which is very famous. It's called the survival shape bias. Survival shape bias. This is basically in World War II. They wanted to put armor on the airplanes, on the aircrafts, in order to increase the chance of survival. So right here, you can see the holes on the returning flights. You can see, oh, there are a lot of holes here, a lot of holes here and there. And now the question is, where I should the armor, right? To make the airplanes better, to increase the chance of returning. Where should I put the armor? Should I just put the armor here? Right here, in this area? Or in this area? Right here, you can see in this area, I can see a lot of holes. And in this area, basically there are no hole. What should I do? Essentially, for this problem, you can see, oh, I want to infer essentially, I want to see the following thing. Right here, you can see the patterns of the holes on the returning flights, but that's not what I really care about. I want to pay attention to the flights that didn't return, right? And then I want to see the reason why they didn't return, and then I want to find a way to solve the problem. So we have to go to the process level. Now, basically, this is a very simplified causal explanation. Being hit and where the hole is are both causes of survival, right? Now we are given So why it's not working? So we are given two things. We are given probability. We are given probability of where the holes. Oh, it's not working. It's not working right. Let me just use my keyboard. So we know the probability of where the hole is, and we know given is survived, right? Given is, oh, this is very bad. So basically, we are given the patterns on the return aircrafts, and we want to infer the following thing. We want to infer the patterns of the holes for the flights that didn't come back, right? And right here, by making use of some other assumptions, we can infer that quantity by making use of this pattern, if you have the process in mind. Okay. When I tested it out yesterday, it worked very nicely. I don't know what happened. I'll figure it out later. Okay, now let's have a look at another example, which is kind of very well known. It's a Monty Hall problem. If you know the problem, could you please just click yes or raise your hand? Whatever is coming up. Oh, okay, good. I see 2, 3, 4. Good, thank you. So essentially, I can skip the example, skip the procedure of the game, and let's just try to give an explanation. So in order to increase the chance of winning money, right, we should change the mind. We should change our mind. Why? You can see right here, where the money is independent from your initial choice, right? Because when you made a decision, you had no idea where the money is. It was random. And then after you see which door is opened by the host, now you can see, basically, you see the common effect. Then the two initially independent variables will become dependent. This means, oh, my initial choice contains some information about where the money is, right? So you should at least rethink your decision. And then after some calculation, you can say, oh, I should change my mind. Okay, so this is basically called by the dependence given the effect, or this is called by the actual information that you can see by considering the effect. So as you can see from those examples, the causal thinking makes a difference. Although in most cases, we just think of the causal information or causality as a kind of background information, right? We make use of causality all the time. And first of all, if you know causality, we can make active manipulations instead of just passive prediction, right? You can change something. You can change the system to achieve a goal. And second of all, you can do generalization or adaptation in new environments. I will give an example on this in a second. And if you know the causal, if you have the causal picture, then you can do information fusion or information integration. So here you can see some examples. Suppose X causes Y and that Y causes Z. Now, what's the relationship between X and Z? You can see, oh, maybe there's another way for X to directly cause Z. But even if that's not the case, I know X causes Z via Y, right? So now you can see you can make the world bigger and bigger by making use of those pieces of causal understanding of the world. And but if you know that X and Y are dependent, and that Y and Z are dependent, what's the connection? What's the relationship between X and Z? You have no idea about it, right? In this case, X, Y dependent, Y, Z dependent. X and Z can be identical, X and Z can be correlated, and they can be independent. So you have no idea. You cannot go from the small pieces of the world to a bigger picture, right? So that's why with the causal information, with the causal understanding, we can go from part of the system to the whole system. And also creativity is basically a causal problem. Usually when, what do we mean by being creative? First of all, you have to ask the right questions. You want to say what if, right? You want to what if something has been different? You want to make a difference. And then you have to answer the question properly. What can I do? So you have to integrate the information from different aspects, right? So here, let me give an example to illustrate the point regarding why some kind of causal information or some particular understanding of the system can be used to improve the prediction performance in some complex situations. So here, in this example, suppose you can see this is my figure, right? This is my figure, and right here you can see my shadow. Okay, in the first scenario, you just see my shadow. Can you say anything about my figure? Can you make prediction from my shadow to my figure? Just make use of your experience. Have a look at questions. Oh, yes. Thanks, Trin. I think that's right. Yeah, yesterday I tried the use I bought something and it worked fine, but now it not work very nicely. So yeah, you're right. I will just do typing. So this is the first scenario. Do you think you can predict my figure from my shadow? Okay. Second, you only see my figure. Of course, this is a new environment. You have no idea where the light is from, right? It's just a new environment. Can you say anything about my shadow if you see my figure? Or could you predict some of it, but not all of it? Yeah, you are right. Because you can just predict some of it. For instance, suppose you want to predict my height. Right? Is the height of my figure or the height of my shadow? Okay, let's just consider that. So in the second scenario, you want to predict my shadow from my figure. Which one do you think is simpler to do according to your experience? Right? You would say, I think most of you might say the first one is simpler. Maybe you can do, okay, if you think the first one, predicting my figure from my shadow is simpler, please click yes. Otherwise, if you think that predicting my shadow from my figure is simpler, please click on no.
Professor, can you please unblock your video?
Yeah, I did that.
Thank you.
Yeah. So okay, now I say yes, yes, no. Good. No. Yes. No. 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 Yes. 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 Okay. So let me give another example, which is similar. Now, suppose you just write down digit 5, right? And then you ask someone to make prediction to see whether this is the 5. It's very easy, right? But now you just ask someone, oh, can you predict the pattern of 5? Basically, my handwritten digit 5 is going to be very difficult, right? If you know the label and want to predict the actual pattern of the digit, handwritten digit, it's going to be very hard. But if you have the handwritten digit and want to predict the label, it's going to be relatively easy according to your understanding of the problems, right, of the process. So essentially, you can see in this case, prediction is not really symmetric. Why? It's because of the changing environment. Here, you don't know, you have no idea about the environment. You don't know where the light is from, right? And from the generative process perspective, you can see my figure is the cause of my shadow, right? This is the cause, this is the effect. And then in any case, the effect contains the information of the cause. I just want to make use of this causal process together with some constraints I learned in my experience to recover the information of the cause from effect. However, right, on the other hand, the effect must contain some information that cannot be explained by the cause, which is about the environment. If I have no idea about the environment, then I cannot predict the effect from the cause very reliably. However, under some very mild assumptions, I can predict cause from effect in a very easy way. Okay, so first of all, this is not rigorous. Second of all, later on Wednesday, you will see kind of a better way to think of this problem. It's not necessary to be causal. We just make use of some dependence pattern in the data. You can say, oh, it's a kind of independence implied by causal process. Usually we say so, but you can, in some cases, even if the system is not causal, you can still make use of this kind of independence or dependence or irrelevance of the modules to make prediction. This is particularly useful for domain adaptation. Okay, questions? Yes, you're right. The light source is unknown. So this is a new environment. You have no idea where the light is from. But still, you can see in the first scenario, you just see my shadow. Then you know the model. Essentially, you know the model. You know mapping from the cause to the effect, right? And then together with some other assumptions, in this case, which are usually the case, you can make prediction. But right here, it's really hard for you to make a prediction because shadow can be everywhere, and the shadow can be long or short. Okay, can you repeat its connection to domain adaptation? Sure. So in domain adaptation, we are given distribution, we are given data generated by one distribution, right? And we want to make a prediction in another scenario, which has a different distribution. What can we do? We have to find and make use of the connection between the two domains, or the two scenarios, right? And just now you can see that in this example, predicting my figure from my shadow is easier than predicting my shadow from my figure, right? So the two variables do not seem to be symmetric in this case, given that the environment is changing. Given that this is a new environment, so you have a distribution shift problem. Now you have to find a connection. The causal direction, this is essentially what we can make use of. So the causal model, causal mapping, or the causal process is rather stable, right? And then you can make use of this understanding of the system. And then you try to identify the source of the change, and then make use of the source of the change and the invariant part to make the prediction. We'll come back to this point on Wednesday. Okay, here you can see some more problems in machine learning. So right here, this is a photo categorization system developed by Google Photos, released in 2015. And right here, you can see right here. I think you can see the mouse, right? No response. Okay, right here you can see. Unfortunately, the African Americans were classified as gorillas. It was such a mistake, right? Huge mistake. Why did that happen? How can you solve the problem? And first of all, you can see, according to the news report, it's not so easy to solve the problem because 2.5 years later, Google claimed that they solved the problem by removing gorillas from the set of labels. So now, gorillas cannot complain, right? That's why they solved the problem. You can see why it's difficult. But for us, right, it's really easy. What caused the difference? So this is another example. I think all of you know this is adversarial attack. So now you can see the panda. But if you add some noise or change some particular pixels, all of a sudden, the machine will say, oh, it's something different. What caused the difference? Why do we have this phenomenon? Why do we have this kind of attack? So essentially, roughly speaking, we have this observation. We have our decision process, right? We understand the scenario, we see something, we make use of experience, we understand it, and then we make prediction based on some features. And the machines use another process to make prediction, to make decision. As long as the two processes are different, then it's always possible to change something so that the decision given by the machine is different while our decision is the same, right? Or in some cases, you can just make the change so that our decision becomes different and the machine's decision is the same, right? In both cases, we say we have adversarial attacks. They are called type 2 and type 1 attacks. So now the problem is whether the machine's decision process and our decision process are consistent in some way, right? So what process do we use? When we see a picture, right, we don't directly make use of the pixels, make use of raw features. We have to find high-level features by making use of our experience. We learn those hidden things first, and then we make a decision, right? So this is different from current machine learning systems, generally speaking. How can we solve the problem? Probably you can just enable the machines to think causally, to think in a generative way, or to think in our manner. Okay. Yeah, we have been talking about artificial intelligence. So traditional machine learning usually assumes that we have a fixed distribution for the data. That's why you can train something on the training set and then apply the same thing to the test set, right? To the test data, because you know all the underlying properties is the same. But in reality, usually most of the time this is not the case. And actually, you can see we human beings can easily do a lot of things, and for machines it's really hard. Right here, if you play badminton very well, right, you can easily learn to play ping pong, and you can easily play ping pong very well, because there's a way for you to transfer the soft skills you have. And right here, in another example, you can see as a human driver, you can make the right decision even if this is a completely new scenario. But for machines, this is rather difficult. So basically, when we say we are intelligent, roughly speaking, we mean the following things. We are able to understand the system. We have our understanding. Here, I'm not giving a definition of understanding. Later, I will try to give some explanation of understanding. Because of the understanding, we can do control, we can do intervention to achieve our goal. And we can decompose a very complicated, very complex task into small tasks, right? We have the modules underlying the complex things. And we can do information fusion. We can just combine the small pieces to form a big picture. And we can learn with few examples by making use of our understanding. And we can do not only interpolation, but also extrapolation, right? In the last example, you can see that even if this is a scenario, even if this data point is not contained in the training set, support of the training set, I can still make use of the information I learned from training set to make a prediction or to make the right decision. How can we achieve those things, right? Maybe you want to keep this in mind, or maybe you have some answers. So how can we understand, or how should we view intelligence? Here, I just want to give a very rather unusual way to think of intelligence. Clearly, you can talk about intelligence in many different ways, right? You can try to achieve intelligence by making use of the by studying, by examining how the brain works, and then try to develop some system like that, right? But here, from this perspective, we want to find the principle, the underlying intelligence. So what's intelligence first? We can think of the problem from the evolution, selection and evolution perspective. Essentially, we want to define intelligence because we have two properties. First, we survived. Second, we prosper, right? And first, that means first, you have a very good ability to make prediction across scenarios. Otherwise, it's really it's not very likely for you to survive across different scenarios. At some point, you can say, oh, all of a sudden you cannot make good prediction, you cannot act properly, and then other species will be more prosperous. So how can you make prediction across all scenarios, across a large number of scenarios? Essentially, we have an inner complex representation of the external world. With this representation, you can explain what you see. You can see the connection between different scenarios, different contexts, different tasks, and so on. And you make use of this complex representation to make very nice predictions. And second of all, we are creative, right? We prosper. We can change the world in the right way to do so, we have to obtain and make use of the causal representation of the world, right? And now you can see, oh, we have the ability to have both of them. And in particular, there does not seem to be a significant gap between the two representations. When we were very young, we couldn't really do interventions, right? In the world, we could only cry and observe and think. And we learned some inner concept representations. And later, we could do more interventions. We made sure a lot of relations are causal, but there's no big gap. That means by making use of the observations and analyzing the data in some way, based on some assumptions, we can find the causal information. So we can go from point 1 to point 2. And also, once we have point 2, we can solve problem belonging to the first category, prediction problems, in a better way. So essentially, we can see how we can learn causal relation and how we can make use of causal relation to solve other problems. Okay, so now let's have a very quick look at the causal graphical model. Do you have questions? If you have questions, you can either raise your hand or say something. Oh, Eric, should we take a break? Can anyone give a response? Are we supposed to take a break here?
Eric don't usually take a break, but
okay.
Yeah. Up to you.
Okay, good. Usually, okay, we'll continue. Okay, let's continue. So, you learn the graphical model. So first of all, let's have a look at D-separation. I want to see whether you learn the concept of D-separation. So if you learn the concept, please just let me know. You can raise your hand. Then I can directly see. Okay, good. Perfect. Thank you. So let's skip this. And intuition, let's skip it. Basically, you can say if X and Y are D-separated by Z, then they are conditionally independent given Z in the directed acyclic graph. Okay, let me ask you a question. What does D mean here? D-separation, what does D mean? Okay, chat window. Dependence. Any other idea? What does D means here? Any other idea? Okay, so dependence is not really wrong, right? But originally D means directional. This is essentially the thing you used for directed graphs. For undirected graphs, the criterion is very different, right? We learned that. So here D stands for directional. That's why you care. It's because you care about the arrowheads. You care about the direction. Okay. We have local Markov condition and global Markov condition. And for DEX, they are equivalent. Local Markov condition says each variable is independent from the non-descendants given its parents. Global Markov condition says that if they are separated, then they are conditionally independent. Now, on the right, you can see some directed acyclic graphs. You learn that. How can you be sure that these kind of graphs represent causal relations? Right? Usually, we use those graphs to as a compact way to represent the properties of the distributions. You can factorize the distribution this way, right? You can see conditionally independent relations this way. How can you be sure that they are causal? Remember, we define the causality in terms of intervention. The causality and the dependence are on different levels. You have to find a way to jump from one level to another, right? To the other. Here we consider 2. What can we do? You have to find a way to describe the effect of interventions. So here, to make sure that this graphical model is causal, we have 3 conditions. And clearly, as you can imagine, we have to make use of the distribution of the data resulting distribution of the variables resulting from intervention. Right here, you can see we do intervention on X. And then we have a new distribution for the variables. And then we can say a directed acyclic graph G is a causal Bayesian network, causal graphical model if those three conditions hold true. The first condition is rather trivial. It says the new distribution is still Markov relative to the distribution to the graph. Means that if they are conditionally independent in the original graph, then they are still independent in the new distribution. It just means that, oh, by this intervention, I will not have any new edge, right? Any extra edge. And the second one says that if you do intervention, then you know the value. If you set the value, if you set the x3 to on, then the probability for x3 to be on is 1, right? This is also trivial. The third thing is rather important. It says that if you do intervention here, say on x3, then other causal modules, for other causal modules, the conditional distribution is the same. So you only, if you do intervention on x3, you only change this module. You cut off all those edges into x3, and you set the value of x3 to on. That's all, right? So right here, you can see two graphs. And on the top, you can see the original causal graph. And on the bottom, you can see the graph after you do intervention on x3. You set the value of x3 to on. Now you can see how you can go from the first to the second. You only cut off those edges. You have the value. And then you can do inference. You can infer the value of the distribution of x5, right, given the intervention. And we can do this operation just because of those three conditions we just mentioned. As long as we have those three conditions regarding the effect of interventions, we say this graphical representation is causal. Okay. Again, if you have questions, just let me know. Otherwise, we'll just go further. Alternatively, here you can represent the causal relation by making use of graphical models. And usually, when you use the graphical model, you also use some conditional distribution to describe the mechanism, right? To see how the causes influence the effect. Alternatively, we can use structural causal model to represent the causal relations, right? So essentially, you can see a set of equations. In each equation, we set the value of the variable, the xi, as a function of its parents and some hidden factor or noise. Xi is fi, a function fi of the parents, and ei. And the ei is the exogenous variable error or disturbance or omitted factor. So now we have a set of equations. If the system is causal, then each equation represents an autonomous mechanism. In other words, each equation is not relevant to the other equations. Although variables can be dependent, each pair of the variables can be dependent, but those equations are not related. This is known as modularity. And this is the most important property of a causal system. And this is also why we really care about the causal understanding of the world, even if you have no idea about the interventions. I don't want to make intervention, right? I just want to make prediction, but still you care about modularity. Because if the modules are independent, meaning that they are irrelevant, I can locate where the changes are. Then I can still make use of my understanding of the other pieces and make the final prediction. So this is very important. Modularity is the essential property of a causal system. And each equation basically just describes how you assign the value to the variable on the left-hand side of the equation. It's structural equation, and that's why it's called structural. It describes the property of the structure underlying the variables. Okay, now, generally speaking, we have three types of problems in artificial intelligence. And later you can see we have more actually. And those three questions are kind of well addressed and are very important. The first thing is to make prediction. On the left, you can see the values, observe the values of three variables at 1, 2, 3. And from this, you can directly make use of prediction, right? You don't have to go to the causal representation at all. This is the prediction. For prediction, you only care about the conditional distribution, right? You can use linear regression, you can use logistic regression, you can use deep network to find some property of this conditional distribution. And the second problem is to make use to predict the effect of interventions. Remember the example I gave, right? You want to predict the effect of a treatment. You want to compare treatment A with treatment B. So here the question is something like this. would the person cough if we make sure that he or she has yellow fingers? So by make sure, here you can see I really do something. It's not just observation. I make sure this, I just change, I just make sure X2 takes this value, and then I want to see the value of the distribution of X3. This is mathematically speaking, here we want to see the distribution of X3 given the intervention on X2 to set the value of X2 to 1, say. So to answer this question clearly, you have to go to the causal picture. You have to make use of the causal understanding of the problem, because essentially, although X2 and X3, right, or in the linear case, suppose they have the same correlation, the dependence correlation coefficient could be the same, right? However, the answer to the intervention question could be very different. If X2 is the cause of X3, then this is something like a conditional distribution X3 given X2. And if X3 is the cause of X2 instead, then this conditional distribution is simply X3, distribution of X3. You can just ignore the condition set, because that intervention will not change the cause, right? So to answer this question clearly, you have to go to the causal level. The last type of question is known as counterfactual questions. So the question is something like this. Would a particular person, George, cough had he had yellow fingers, given that he doesn't have yellow fingers and coughs? So right here, if you compare this question to the second question, you can see we have more information. First of all, we want to see the interventional effect. We want to see the effect of intervention on this guy to make sure that he had yellow fingers. But here we have a condition. We observe something. We observe that the same guy does not have yellow fingers and that he coughs. We can go further, because now we can infer in the second type of questions, we just want to infer something regarding the population, right? I have no idea which one you are talking about, which particular object you are talking about, or subject you are talking about, or person or unit you are talking about. I just want to give a prediction regarding the distribution, or based on the distribution. But in counterfactual reasoning, we know what we are talking about. Maybe you are talking about this particular person or this particular day. You observe something, and then you want to see the effect of interventions. Okay, so you have more information. You can have a better way to solve the problem. Okay. First, let's see how we can identify causal effects. And you know the golden standard to identify causal effects is to make use of randomized controlled experiments. If I want to see the effect of treatment on recovery, or if I want to see whether treatment has an effect on recovery, what can I do? I have two groups of patients, right? For one, I have to guarantee the following thing. Apart from treatment, this variable, all the other variables must either take the same value or the same distribution across the two groups, right? They either have the same value or they have to follow the same distribution and vary at random across the two groups. Then, if I observe some difference in recovery, I know this must be caused by treatment. And then I can say, oh, treatment has an effect on recovery. And then you can see that it's really hard to do this kind of experiments, because you have to make sure the patients in the two groups have exactly the same value for the other features or the same distribution for the other features. How can you guarantee that? Especially in many cases, you have no idea what other variables you have to consider, right? How can you do this alignment? Then we have to solve the problem by making use of our causal understanding and observational data. And sometimes this is known as observational studies of causal effects. Or generally, we just say identification of causal effects. But sometimes people also say it's causal inference problem. In contrast, next time you will see, we'll talk about the causal discovery. Causal discovery aims to discover causal information by analyzing data. They are very different. They are two fundamental problems in causality. Okay, so why do we care about the causal effect? In this example, remember this example, right? Simpson paradox. You can see if you make prediction just a prediction. You make use of a conditional distribution of R given T right here. You want to see the given this treatment, you want to see the effect of a treatment on recovery according to the distribution, and this is the only prediction. And this is the rule, chain rule and sum rule, right? If you want to see the effect of treatment on recovery, what can we do? You have to make use of the distribution, probability distribution of R of recovery given the intervention on treatment. And this describes the property of this particular causal link right here. This causal link. I only care about this one. That's why I do intervention. I don't care about any other factor. Given a patient, I just do intervention, and then I want to see whether intervention will make a difference in recovery. This is what we want to find. How can you find this quantity? How is this quantity different from the conditional distribution? That's the essential question, right? So you can see, according to the definition of intervention, when you do intervention, you cut off the edges into this guy, right? So this edge is not there anymore. If you don't have this edge, then this conditional distribution, probability distribution of stone size given treatment will become the marginal distribution of stone size. Because after you cut this guy off, stone size and treatment will be independent, right? So in order to find this causal effect, we just need to, in this example, we just need to replace this conditional distribution with this marginal distribution. Is that clear? As long as this example is clear to you, then we can quickly go through some techniques. Why did the variable you are summing over change from S to R? Oh, I'm sorry. Wow, this is a stupid mistake. It should be S right here. It should be S. Sorry. Yes, you are right. Thank you very much. Right here should be S. Let's see what I can do. Oh. Yeah, this should be S. This R should be S. Okay. Apart from that, is this example clear to you? Okay. So now, questions. What is PS given T? Okay, so suppose you want to find the marginal conditional distribution, should S be parent of T? No, this is just the application of the, this is nothing but the application of the sum and the product rule in probability theory. I want to predict R from T. I want to predict recovery from treatment. Then basically this is implied by the conditional distribution, and this is how you calculate the conditional distribution from this conditional and this conditional. Application of sum and product rules. Okay, standard thing. No other question? Let me just go further. Now let's have a look at this picture to see why we have that phenomenon. We have this paradox. So right here in the blue line just indicates the recovery rate of different treatments for different groups, right? Here, treatment A, this is for small stone group. Treatment A is better than B. And the red line shows the recovery rate for the large stone group. A is again better than B. However, here I have a lot of patients. And right here, a lot of patients with small stones receive treatment B. We have a lot of people here, we have a lot of patients here. As a consequence, when you use the product and chain and sum rule to calculate conditional distribution, essentially you just take the average across all patients. As a consequence, right here the mean will be close to this guy, and here the mean will be close to that guy. So you can see very different pattern if you calculate the conditional distribution, right? And if you do the marginal distribution of S instead, you don't care about the size anymore. As a consequence, you see this. So this is a probability or expectation of R given intervention on T, right here. You can say, oh, A is better than B, right? Because now you use the same weight to take the average, which is PS, not PS given T, not the probability of stone size given treatment. This is the difference between conditioning and manipulating. If you do manipulation or if you do intervention, you have to cut some edges off, and then you can, the expression could be very different. And this is what you care about if you want to see the causal effect. What's the definition of causal effect? Essentially, it's just the probability of the target variable given intervention on the variable you can do you want to change. So the probability distribution of y given to x, and you can understand this quantity very intuitively. To do so, you do intervention, you cut those things off, right? You just directly set the x value to some specific value, and then you want to infer the probability distribution of y. This is a basic definition, and in some cases, maybe you just care about the average effect. That's the expectation according to this distribution. Expectation y according to this distribution. So if you know this distribution, essentially you can derive other measures. Second question is whether this causal effect is identifiable. This is a very fundamental question in causality, and a lot of researchers in statistics and as well as computer science still do research in this direction. So given, what do you mean by identifiability of causal effects? This is the setup. We are given two things. First, you are given a causal graph, qualitative graph for the process. And then you have observational data or observed data for some variables, for the observed variables. In this case, suppose we don't observe stone size, but only treatment and recovery, right? And this is hidden. Now the question is whether you can recover the influence, the causal effect of treatment on recovery. So the identifiability is defined this way. It's the same as the identifiability of parameters in statistics. Given the same causal structure and the same distribution for the observed variables, you want to see whether the result for this quantity distribution of y given to x is the same across all possibilities. So you can have different models, right? Suppose you have two different models, different underlying processes with the mechanisms. And suppose the two models have the same causal structure and the same observed data for the observed variables, only the observed variables. If you observe everything, then it's always identifiable, right? We only observe the data for those two variables in this example. Then you want to see whether the two models will give the same answer to this question. If they give the same answer, we say, oh, the causal effect of x on y is identifiable. If they don't, you say it's not identifiable. Then this quantity may not make sense because you don't have a unique solution. Okay, so that's the identifiability. And then in this example, you can see the key issue to answer the question is to control the confounding bias. In this case, if you don't observe the age group, then essentially it's not identifiable. So under what conditions is the causal effect identifiable? Here I'm going to give two criteria very quickly. They are very popular in the field. The first one is known as the backdoor criteria. So here we have ordered pair xi and xj. We have set of variables z. Let's consider a specific example. Suppose z is x4, single variable. We say z satisfies the backdoor criterion relative to the ordered pair xi, xj if two conditions hold true. The first one says that no node in z is the descendant of xi. That's why it's called backdoor, right? So this is not the effect of xi, can only be in front of the backdoor of xi. And the second one says that z blocks every path between xi and xj that contains the arrow into xi. This just means that, oh, Z blocks every backdoor path between X and Xj relative to Xj, to Xi. So right here, we only care about those paths into Xi, which are called backdoor paths. Now let's verify whether this condition those two conditions hold true for different sets of variables. What if Z is X3 and X4? If Z is X3 and X4, do you think Z satisfies the backdoor criterion relative to Xi, Xj in this example? If your answer is yes, please click on yes. If the answer is no, just click on no. I want to see how many of you have an idea about it. Okay, yes, wonderful, yes. And let's consider another example. Thank you. Suppose Z is just X4 with a single variable X4. Do you think Z satisfies the backdoor criterion relative to ordered pair Xi, Xj? Yes or no? If you provided answer before, please change your answer. Okay, some said yes, some said no. So here, let's have a look at this example. Given X4, you can see, yes, this path is blocked. However, this path, Xi, X3, X1, X4, X2, X5, Xj, this path, M path, is open if you condition on X4. Z4 does not, right, according to this separation, Z4 does not block this path. That's why for this set of variables, Z, it does not satisfy backdoor criterion. You can check the, you can have a closer look afterwards. And then if Z satisfies the backdoor criterion relative to XY, then the causal effect of X on Y can be characterized this way. So essentially, you can see the only difference from the conditional distribution of Y given X is to replace the conditional distribution of Z given X by the marginal distribution of Z. Okay, have a look at this equation later. This is the front door criterion. And you can see from this example, from this graphical representation, it's very clear. Right now, we care about the front door is in front of X relative to Y. You have to, if you want to go from X to Y, you have to go through Z. That's the essential criterion, essential condition. So Z intercepts all direct paths from from X to Y. No backdoor path from X to Z. No backdoor path right here. You can have backdoor path from X to Y, as you can see from this path. Suppose this is the unobserved common cause or confounder, right? You have backdoor path here. And all backdoor paths from Z to Y are blocked by X. And then we can say Z satisfies the front door criterion. And then we can do another, we have another way to do correction. Right here, you can identify causal effect of X on Y this way. Okay, some of them may know something about ignorability. So in potential outcome framework, right, people use the ignorability or conditional ignorability to specify the condition under which the causal effects are identifiable. Actually, they are equivalent. Let me just give some very quick explanation. This is a backdoor criterion, and if Z satisfies backdoor criterion, we say the causal effect of X on Y is identifiable. So according to ignorability, the condition is that follows: Y small x is independent from X given Y. So here, Y small x is a random variable. What random variable is this guy? First, we have, according to the potential outcome framework, we have Y as a function of X and U. X is the value of some particular random variable, right here, particular cause. U is the specification of the unit U. Could be a particular person, particular day, right? Particular scenario. So this is the Y as a function of small x and U is a value attained by Y, variable Y, in unit U, for instance, for this particular person. Under intervention on X. So right here, this is the value of Y after you do intervention on X for this particular unit. And now you can just ignore the unit. And this guy will become a random variable because the value could be different. It varies across different units, different persons. So Y as a function of small x is a random variable. It's called a counterfactual variable. And Y given small x, what's that? You can think of Y given small Y as a function of small x as a description of the causal mechanism from X to Y, right? So all the factors that are involved in this process will influence this random variable. And ignorability says that Y given small x is independent from X given Z. What does it mean? Look at this picture. So Y given small x basically is a causal mechanism involved from X to Y, right here. And this is X. If Z blocks the backdoor paths, then given Z, how the random variable X would be independent from Y, from how Y is generated from X. Although X and Y are dependent, right? How Y is generated from X as a causal mechanism will be independent from X given Z, right? The two processes are not related if you condition on Z. Questions? Oh, no, we are going to stop. So this is ignorability, and now you can see basically they say the same thing. If they satisfy this criterion, and then we have ignorability, and we can identify the causal effects. So potential outcome framework and the graphical criteria are somehow consistent, but there exists some very subtle difference. I'm not going to talk about the difference, but basically you have a very rough and fundamental understanding of the criteria given in different disciplines or in different by different people. Daniel Rubin from Harvard developed a potential outcome framework, and Luda Pearl from UCLA, as well as Peter Spertis and Clark Glimmer from CMU developed the graphical criteria for identification of causal effects. Okay, so I'll stop here. Next time, at the beginning, you will see a unification of the criteria, and then we'll see how and why we do counterfactual reasoning, and then we can see how we can discover causal information from observational data. Okay, thank you very much.